So the key thing that's usually missing, actually up to now, in most of the game theory that we talk about, is that we have a well-defined game with a fixed number of players. If you go to eBay and try to bid, you don't know how many players you're going to face. Even in this classroom, you may not exactly know there are 16 or no, there are 17 players that are awake and are going to play this game. Population uncertainty is a problem, especially say in voter turnout games, for example. Well, we know that the presidential election of Taiwan is coming up in January. Do you know exactly how many voters are eligible to vote in that election? No. But in our voting games, well, we assume people know the number of players, know exactly the number of voters. That's, of course, not a realistic assumption. You actually play a congestion game every day when you go out during rush hour. Should you take this route or that route? Well, there's a mixed strategy equilibrium there. You have to decide which route to take, and if too many people are going this way, then it takes like 3 hours to get home. There again, we have no idea how many cars or other vehicles are playing this game with you. You may have an idea, but not exactly. I actually faced this problem during the long weekends, because during long weekends you have to decide whether or not which highway you want to take to go from, say, Taipei to Kaohsiung and so on. And of course, if too many people are on, say, the Zhongshan Highway or Highway number 1, then it'll take forever. But if too many people think that there are too many people going on Highway number 1 and take the alternative, then of course this alternative will face congestion. So there is actually game theory with population uncertainty, pioneered by one of my heroes, Roger Myerson, who also won the Nobel Prize, which tries to model these what he calls Poisson games. So instead of fixed number of players, there's a Poisson distribution number of players. So the number of players, big N, is a Poisson distribution that follows this. The parameter for a Poisson distribution is this lambda, or this, which equals to the mean and also the variance of the Poisson distribution. The first one is what we call environmental equivalence. The other is independence of action. Environmental equivalence means this. Suppose, so the Poisson distribution has this property, it's that two independent Poisson distributions would add up to another Poisson distribution. And what's good about that? Well, if I'm playing heads and tails half-half, and you are also playing heads and tails half-half, then I could actually sum up. So if I could actually sum all of this up. So what's going to happen is that if I know there's a Poisson, say, of Poisson 20 number of players in this game, everybody playing, say, half-tails, half-heads, I can actually know exactly the distribution of heads being played and tails being played. And that's very good to actually sum everything. The other one is environmental equivalence. What does this mean? When we play an auction, say we have, say, 10 players, what this means is that I'm facing 9 or 10 minus 1 opponents. It's very hard to keep track of the n minus 1. The fun thing for the Poisson game is this. If you are playing in this Poisson game, conditional on you are in the game, how many opponents do you have? And the answer is, if you're playing this Poisson game with a Poisson n distribution of players, conditional on you are in the game, you are facing the same Poisson n number of opponents. So if you think of your, when you first learned the Poisson distribution in your statistics class, the typical example for the Poisson is that it has this memoryless property that conditional on you are waiting for the bus. Conditional on you already waited for 10 minutes. How many more minutes are you going to wait? Then with the Poisson distribution, you have this memoryless property that conditional on you waiting for 10 minutes. Well, the amount of the additional minutes you have to wait is still the same Poisson distribution as you waited 0 minutes, and so it's independent of how long you have waited. And so the same thing happens here, that conditional on you are in the game. Well, the number of opponents you're going to face is still Poisson n. So this is what we call environmental equivalence. Meyerson applied these to voting games and to contests and other things, and so we're going to try to apply this to a real world of field game that's actually played. So the question we're going to see is where would this Poisson game be relevant, and how good does Poisson equilibrium fit the data, and then we'll see how do we get to the equilibrium. And so this is the game that was actually played in Sweden. This was played in 2007, between January and March. They played one game a day, so they played for 49 days, or actually, so they played for actually more than 49 days, but in the 8th week, there was this news that people were colluding in this lottery, so that they stopped it sort of unexpectedly. So we got the first 7 weeks of data. In each day, what you do is you pick one number between 1 to 99999. So you pick one integer, and whoever chooses the lowest but unique number wins. And you are playing against, on average, 53,000 Swedes. So let's just assume that it's a Poisson distribution of Poisson with a mean 53783. Yeah, so please take out one piece of paper, write down a number. If we only have this many people, let's just play 1 to 99. So pick one number, 1, 2, 3, 4, 5, all the way to 99. We don't need to go up beyond 100. So pick one number between 1 and 99, and whoever picks the lowest but unique number wins Dr. Sinatsen. And I'm going to play as well, so I have to write down my number someplace. I'll count from 1, 2, 3, all the way up. When I say 1, if you picked 1, raise your hand. And if you see somebody else also raising his or her hand, then please put your hand down, and I'll keep counting. Okay? If you pick 1, please raise your hand. Nobody. 2 of you. Okay, thank you. If you pick 2, please raise your hand. Nobody picked 2. I should have picked 2. If you pick 3, please raise your hand. Too bad. 4. Thank you. 5. I should have picked 5. 6. 6 once. 6 twice. 6 won last time, right? Should you pick 6 again? No. Why not? Oh yeah, 2 and 5 did not. Nobody won, right? 2 and 5. I should have picked 2. Well, the problem here, of course, is that if everybody thinks that they should pick 2, and yeah, so you know that nobody picked 2, nobody picked 5, and 6 won last time. Should you pick these numbers now if you play this again? It depends on, well, it depends. And actually, there are a lot of what we call unique bid auctions that actually run. These sites come and go, but there are a lot of these websites where what you want to be is the lowest but unique bid, and you actually could win an iPhone for like 35 cents or something. Yeah, so there is ongoing study on that, and there's even interesting Thanksgiving with Ozzy. So one winner and 3 friends will share Thanksgiving at Ozzy's new house in LA, and so you have to put in your bid in cents, and you could actually win. And also, this is a very interesting situation where you could actually test theory, because you have very well-defined rules, and you could solve for the equilibrium. And also, you could actually replicate this in the lab and to actually see what happens. So first, how do you solve the equilibrium of this game? Well, hint, this is the lecture on weak strategic equilibrium. So yeah, so we have to, there is no pure strategic equilibrium in this game. Well, actually, put it this way. So if you think of asymmetric equilibrium, you could have say, okay, I'm gonna pick 1. Don't mess up with me. Everybody just picks some random number above 1. That is an equilibrium. And of course, if you have a known number of uncertainty on how many people coming in, this equilibrium would not work, because some random person would not pay attention to my announcement and pick 1, and I'm dead. Okay, but with population uncertainty, well, you have this unique mixed strategy equilibrium. So what you want to, the winning probability for picking any number is that you are the only person who picked that number. And nobody picked 1, 2, 3, all the way up to k-1, the number below it. So what this means is that, and this is the Poisson probability for nobody else picking 1. And then this has to equal to the winning probability of choosing 2, which is nobody choosing 1 uniquely, and nobody choosing 2. So nobody is choosing 1 uniquely, and nobody choosing 2. And the same thing, if this has to also equal to nobody uniquely choosing 1, nobody uniquely choosing 2, and nobody choosing 3, because that's the winning probability for me to choose 3. And this has to equal to the winning probability for me to choose 4, which is nobody choosing 4 and nobody uniquely choosing 3, 2, 1, and so on. So here I have a whole bunch of equations, and then the probabilities, P1, P2, all would have to sum up to 1, and I can solve. Well, actually what we did was we had MATLAB to solve this for us. This is the unique Poisson equilibrium for the Swedish game. You basically pick 1 with the highest probability, although it's very small, and then you sort of pick almost uniformly, but decreasing all the way up to close to 5,500, and then it quickly drops down to almost 0. So the probabilities are decreasing, and but you have full support, so these are almost 0 but still positive, and it's sort of concave over here and convex over here. And the last thing is that if the average number of players goes to infinity, what you do is it converges to uniform. The Swedes do. Well, let's take a look. This is the actual data for the first week. Actually, so some of these numbers go off the roof. So some numbers are chosen more than 150 times in the first week. And then, so what you see here is that small numbers are overchosen by a lot compared to equilibrium. There should be a lot of choices that will be between 2,000 and 5,000 that are underchosen. And then the numbers beyond 5,500 that should almost never be chosen are still chosen by a lot. This is 6666. This is 7777. Apparently, there are so many Chinese or Taiwanese in Sweden that there are a lot of 8888. Why is that? It's ba 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 ba. That's the lucky number in Chinese. And there's also 9999 over here. So week 1, not pretty good, not really good. Well, but we have 7 weeks of data, right? So let's see how this proceeds. So I'm showing you, because there are also weekly cycles, I'm showing you week by week. So this is week 1, now we can get to week 3, week 5, and now week 7. This is the last week we have data on. What you see here is that the small numbers overshooting are now all gone. The gap has filled up all the way up to, well, there's still a gap over here. So if you chose like 5,000 to 5,500, you still have a very high chance to win compared to other numbers. And the high numbers are almost never chosen anymore. Although you still see a little bit of 6666, some 7777 is still persistent, 8888 is still visible, and 9999 is barely visible. So you see people converging towards the equilibrium in this 49 days of play. Unfortunately, this field game ended in the 8th weeks, in the middle of the 8th week, so we do not have more data to see if people further converge or if people fluctuate. But we do see a very clear pattern that people are converging towards the equilibrium. What's more, there's actually small details about the game. The first thing is that you're allowed to bet up to 6 numbers. Although in the data, we could not see which person betted how many numbers. So this could alter the theory prediction. The other thing is that the first prize actually fluctuated quite a bit because it's guaranteed to be at least 10,000 euros, but it actually depends on how many bets there are on it. And there are actually, so if you tie, then you're allowed to share the prize. Suppose nobody's unique, now what happens? In our theory, if nobody's unique, then nobody wins. But what in the rules, in the lottery, what they did was, if nobody's unique, then we have the lowest pair who tied would share the prize. Or if there are no pairs, then say everybody picking 1 and only 3 guys picking 2, then it's the lowest trio that's going to share the prize, and so on. Although this never happened, but the rule has a small detail that's different. And also, there are actually also smaller second prize and third prize. So if you're close to the unique number, if you are the unique number, you get the big prize. But then if you're close to that, then you get small prizes. So yeah, so there are these small details here. And so, of course, the empirical question that's really burning here is that we impose the Poisson assumption. And of course, that's not true here. Well, if you actually calculate the variance and the mean of the distribution of number of players in this 49 days, it's not Poisson. It's not a Poisson distribution. And of course, we can't verify if people believe that it's a Poisson distribution or not. So here we are opposing a lot of assumptions here. We are simplifying. But and also there are these puzzles here, like this. I love this. So 1950 plus and minus 50. So you see a bunch of people picking numbers over there. Our guess is people are guessing their birth year. Although 1930 is a slump, it is significantly lower than 1929 and 1931. 1940 has much fewer picks compared to 1941 and 1939. 1950, 1960, 1970, these whole numbers somehow have these drops that somehow I believe that my birth year is 1970. Oh, that's too common, or too many people will pick that, and so I would avoid those numbers. What we did was we tried to replicate this this entire experiment in the lab. Now this was done in UCLA because back then I was still there. And we did this 1 to 99, and with, again, 49 rounds, we want to replicate what we saw in the field. And what we did was, so here we announced the winning number, and that's the only thing that people know. And we scaled down the prize and the population by 2,000. So the initial prize was 10,000 euros, so we scaled that down to be $7 US. That was the that was 5 euros back then. Now, of course, it's not. And we divided the 53K average number of players by 2,000 to get an average of 26.9 players in this game. In several sessions, we made a mistake so that the variance is smaller than the Poisson, although we did not tell them it's Poisson. And then in the last session, we actually told them it is Poisson, and we made it to be Poisson. And we don't see any difference, but this is the data that we see. The bars are the data. So again, we see overshooting of small numbers, undershooting of intermediate numbers. Yeah, people love 17, right? So yeah, so these prime numbers are overchosen, even in this data. And you do see some interesting fluctuations across weeks. In week 1, yeah, 17 was chosen by a lot. That's 11. So 11, 13, 17 were chosen by a lot. And well, people aren't choosing enough, and then people overshoot and then undershoot and so on. So there's a lot of fluctuation in the data. So we could reject the Poisson equilibrium, because what I'm showing here, this is the equilibrium prediction, and the green line and the blue line above and below are the 95 confidence interval for the Poisson distribution. And of course, we have a lot of bars below the blue line or above the green line, so we know it's not equilibrium even here, even in the lab, in the best case where we control for all these other small details. So we can still reject equilibrium. If you want to learn here, there's nothing to reinforce, because only the winner is reinforced, because he wins, everybody loses. You can't really update on what other people are doing, because you only know the winning number. You have no idea how other people chose. You only know that, oh yeah, somebody uniquely picked 1 or picked 3 last time. Note, this is slightly different from how we did it in the class, because in the class we actually know that, oh, so 2 people picked 1, nobody picked 2, and 3 people picked 3, and so on in the classroom. In the actual experiment, we only said, oh, 6 won last time. 6 is a unique number last time, and so now what do you want to pick? So here's the graph. So this is the median of all of the past winning numbers. That's the black line over here. The dotted line is the median guess, and so what you see here is that the median guess is tracing the median winning number. So you do see something going on there. What this means is that there should be some kind of imitation learning that's going on to try to explain this. So remember, week 1, there's overshooting in very small numbers, under choosing intermediate numbers, and then over choosing large numbers. Yeah, so the way we did imitation learning was to try to fit the first week with the field data and then try to have it learn. And what we can see is that, yeah, so it does work by, so imitation learning tries to trace what you see week by week changes all the way up to week 7. So, the imitation learning model does try to, even though I did not tell you the detail, we could try to find a model to try to explain why people are converging to what the Poisson equilibrium is predicting, at least for the first 7 weeks of data that we have. So yeah, so this is some evidence on, yeah, so people are imitating the winners here, or close to the winner, and trying to win. This will actually tie to a further lecture when we get to dominance of the games. So we haven't talked about the detail here, but here let me show you what we actually did. So we developed this idea that, hey, suppose you are level 1 facing a whole bunch of random players. What would you play? Well, if you believe your opponents are randomly picking numbers between 1 and 99999, what should you do? Well, pick 1, because 1's going to win for sure. Or 1 has the highest probability of winning, because it's the lowest number. And well, you have the same if your opponents are picking randomly, well, the probability for having any number to be unique is the same, because of the randomness. And so picking 1 will give you the highest winning probability. Okay, so how about this? Let's allow for some noise. So level 1 is not always all choosing 1. They're choosing close 1 and numbers close to 1. Then you may not want to choose 2, but maybe you should choose, say, on average 3 or 4 or something like that. And then, of course, you can think of, what about level 3? Thinking that there's a bunch of level 0s, some level 1s, some level 2s, and so on. And then you might want to choose even higher numbers. And so, okay, so what we built was this cognitive hierarchy model where, so zeros, level zeros choose randomly. Higher step thinkers best response with the belief that there are a mixture of lower types. This type distribution is a Poisson distribution because that's what the cognitive hierarchy model of in the literature that they choose. That's also why I love Poisson. And so what this means is that if I'm level infinity, I know that the whole distribution is a Poisson distribution. But if I'm level 3, I only know there are level 0, level 1, level 2, and that's it. So that would be a truncated Poisson distribution. So if I'm a higher type, then I'm approximating the entire Poisson distribution. But if I'm a lower type, then I only know types below me. At some sense, this is what we call a cognitive hierarchy because there is an upper limit of how many levels I can fit. And so this is a sort of exogenous bound. I cannot imagine people above me. That's the cognitive limit. Okay, so what we did was we fit this data not with best response, but with this noisy best response using a power function, and so we could estimate the average number of thinking steps, average number of levels of the data, and also we could estimate how noisy is the data. So here the precision parameter is lambda. When lambda goes to infinity, you are best responding. If lambda is 0, then it's completely noise. Yeah, so here's your level 0, that's choosing randomly. Level 1 picks one with the highest probability, but then chooses also some numbers that's close to 1. Level 2 peaks at, say, 5 or 6. But then for level 3, you know that there's a whole bunch of 1s, whole bunch of 5 or 6, that you want to pick something in between, and also something slightly high, even higher, and so on. So you have a whole bunch of these levels. So comparing the actual data and the Poisson equilibrium, when we fit the model with the first week data, we get a lambda of 1.8, meaning that the average number of steps of reasoning is only less than 2 steps. So the majority of people are level 1 and level 2s. And yeah, so that could create a distribution that sort of mimics what we see in the data, overshooting small numbers and undershooting here, even though there's still a lot of other deviations that we do not capture. You can also try to do quantum response on this, but quantum response does not really work here. If this is the Poisson equilibrium, what you see is that the quantum response approximates the equilibrium from below, so you cannot explain the overshooting. Yeah, this is the actual data that you can see. So when we increase the precision, well, we are approximating the Poisson equilibrium from below. So that's not good. Okay, so to conclude, what we have here is a well-defined game that's actually played in the field. And so we fit the Poisson equilibrium to the data. Again, just like what we saw in the lecture on mixed strategy equilibrium, this is another game with mixed strategy equilibrium. And it seems that the frequencies are reasonably close to what the data looks like, although deviations are still significant. Because we have 49 days of the data, we could actually fit a learning model to try to describe this convergence. This is slightly different from what we see in the games with mixed strategy equilibrium, because if you pull all the data, then of course you don't see anything, because that's the whole data set. And to explain what we see initially, we have this cognitive hierarchy model where a reasoning step of average of 1.8 could explain the overshooting of low. And of course, the next problem is, can we go on to look at other population uncertainty games? We actually did a Poisson lowest unique bid auction paper, a theory piece to explain what we see in unique bid auctions. But we haven't started to do any further experiments, but you can think of other applications.